History records that there were three apples that changed the world: Adam's apple, Steve Jobs' apple, and Newton's apple. Whether it really fell on his head or not, you can't be sure, but what you can be sure of is that that apple led to great things like the Hubble telescope and Wi Fi. That all came from his universal law of gravitation, F is equal to gmm by r square. And it is from this equation that we can find the acceleration due to gravity, g, which comes up to 9.8 meter per second square or 32.2 feet per second square. So g is supposed to be constant wherever we go on the surface of the earth, like an apple would follow the same rate anywhere, from the Sahara Desert to the North Pole. But that's not true. Thing is, we always want our calculations to be simple. So when we try to find the value of g, we consider the earth to be a uniform sphere, but it's actually flat at the poles and kind of bulging out where the equator is. And because of this weird shape, which is called an oblate spheroid actually, there's a difference in the radius of the earth at the equator and that at the poles. It's a big one actually, around 21 kilometers. But then again, when you compare it to the accepted radius of the earth, that's 6400 kilometers or 3977 miles, you would pretty much understand that that's really not much of a big deal. But every little bit counts, so there's a difference in the value of g depending on which country you're in, even if you're at the same height above sea level. Let's go back to what Newton said. F is equal to gmm by r square. Now with a little manipulation, you get another formula. G is equal to gm by r square. So as you can see, the acceleration due to gravity is inversely proportional to the square of the radius. So if g increases, r decreases. Let's go back to the oblate spheroid that we call home. Earth bulges at the equator, so obviously the equator is farther from the center of mass than the poles. So r of the equator is greater than r of the poles. So what do we get? The acceleration due to gravity at the poles is greater than the acceleration due to gravity at the equator. So you think that's that and the story is over. But not so much. See, we've discussed what happens to g due to the shape of the earth, but we haven't said anything about the fact that the earth rotates on an axis. What about that now? Let's consider a monkey, little Mickey, on the surface of the earth. Now, Mickey has a mass m. The earth exhibits a rotational circular motion, so it's obviously going to have an angular velocity omega. Then it'll have a centripetal acceleration 2 omega square r. This is directed towards the center of the earth. So the centripetal force on Mickey would be m into omega square r, again towards the center of the earth. Now where there's a centripetal force, there's a centrifugal force. This force would be directed outward. Then we have the gravitational attraction mg towards the center of the earth, because gravitational forces are always attractive. Since the earth keeps rotating and so many forces thus act upon it, the resultant gravitational attraction thus changes. Now to find the actual gravitational attraction mg star, we take the vector sum of mg and m into omega square r. Simplifying, this comes out to give g star is equal to g minus omega square r cos square lambda. So here, lambda is the angle from the radius and the line joining the object to the center. So if we took lambda would be 0 degrees and thus cos lambda would be 1, giving g star is equal to g minus omega square r. Now this is the minimum possible value of g we could ever get. Now, if we took Mickey to the North Pole, we'd get lambda as 90 degrees, giving us cos lambda as 0. So the whole term omega square r cos square lambda would get cancelled, giving us g star is equal to g. This is the maximum possible value of g because nothing's subtracted from it. So hypothetically, what if the Earth stopped rotating completely? Now there's no rotation, so there's no angular velocity, acceleration, centripetal or centrifugal force at all. So omega 0, then omega square r cos square lambda would be 0 too. So at the equator, G star is equal to G. Now since the term subtracting stuff away from G is 0, you'd see that G star would increase after the Earth stops rotating. At the poles, G star would still be G, no change there. Taking our example, if the Earth stopped rotating, Mickey's weight in Brazil would increase. But on the poles, it would stay the same. So, before I leave you, I'd like to ask you a question. Newton said that every body in the universe experiences an attraction to another body. As we saw above, gravitational attraction and centripetal force are two different things. However, another force can substitute as a centripetal. For example, when a car turns on a road, the force of friction between the wheels and the road provides a centripetal force for the car, which stops it from going tangentially and hitting whatever's near it. So now, the Earth revolves around the Sun, and every year it completes one revolution. There's a centripetal force involved, and obviously there's gravitational attraction. Now, is the gravitational attraction of the Sun on the Earth equal to the centripetal force, or is the gravitational attraction of the Sun on the Earth the actual centripetal force? And because of this year-long revolution, does G change? Think about it.